Hello, everyone. My name is Yasith Jayawardana, and I'm a PhD student in the Department of Computer Science at Indian University. Today, I'll present you our paper, StreamingHub, Interactive Stream Analysis Workflows. Research is cumulative in nature. We reuse things that people have built in the past so that we can do new things based on our prior knowledge. However, when doing cumulative research, you almost always have to reuse some code base or experiments that people have done in the past. But if these codes are not commented properly and the instructions for reusing them are not given explicitly, sometimes it's very difficult to try and reuse past work. So essentially, this hinders the reusability of code and data. On the other hand, if you're trying to replicate an experimental study, if the key information that's needed to reproduce the experiment is missing, then the experiment essentially becomes hard to reproduce. And even for things like algorithms, if certain parts of the algorithm are not documented and explained properly, others may find it really hard to reproduce the results that the original authors got. So essentially, this hinders reproducibility. So reusability and reproducibility are two very important things when it comes to verifying experimental results. In the past, people have come up with principles such as FAIR, which tries to make data reusable by having strict guidelines for metadata. Also, when it comes to managing large code bases that are iterated over several years of work, scientific workflows play a very important role, where it abstracts away the different parts of the code in terms of functionality. Scientific workflow systems run scientific workflows designed in this manner to make reproducible experiments. So overall, these things work together to make sure that reusability and reproducibility is present on experiments. However, there's still a problem. For instance, if you take applications like stream-based eye tracking, having reusable input data does not still guarantee that whatever output data that's generated in real time is reusable. So you may generate the outputs and have to end up making these outputs reusable, which is essentially a manual process. So in this work, we explore whether we can propagate metadata from inputs through reproducible experiments so that this manual effort is alleviated. So our focus was on real-time stream-based applications like eye tracking. So for these tasks, we identified few ingredients that let us propagate metadata through experiments. So the first is a metadata format that enables reusing data. Second is a scientific workflow system that lets you build reproducible experiments while using these metadata formats. And third is a tool to read and write file data as streams. So for the metadata format, we propose data description system, which collectively describes data sets, data streams, and data analytics. The key information that we require in this format are given on the image shown on the right. For the scientific workflow system, we opted for a system that provides visual workflow design as it lowers the technical barrier for experimentation. And as such, we selected Node-RED to design, execute, and monitor workflows. To read and write file data as streams, we propose data marks, which lets you stream data into workflows in 3 modes. First, it allows you to replay stored file data. Second, it lets you simulate synthetic test data so that you could verify your workflows in terms of test cases. Third, we provide way to stream real-time sensory data through the live mode. Based on these, we build a metadata propagating interactive stream analysis framework, which we term StreamingHub. Now let's look at the StreamingHub's architecture. StreamingHub consists of 4 main components. First, you have the data description system, which is essentially the descriptor for different types of data. So it contains information such as what fields of data are coming in and what kinds of streams are generated from a particular set of files. Next, we have the data marks, which essentially takes these data sets and data sources and converts them into streams that are readable by the workflow designer and the operations dashboard. So the workflow designer is where you design the workflow for a particular experiment, regardless of what data you receive. It basically works by dragging and dropping different nodes into a canvas and then connecting these nodes on the canvas together so that you end up in a workflow. So simply by looking at the workflow, you could say how data flows from one node to another and what kind of tasks are performed on these real-time data streams. Next, we have the operations dashboard, which provides an interface to control these workflows and start sending them data and observing the outputs generated by the workflows. So here you could see that it allows you to make selections on the different data sources that you want to send into the workflow. And also, once you start doing that, what kinds of outputs that come through this workflow in the form of visualization. We conducted 2 case studies to show the utility of StreamingHub. First, we did an eye movement analysis study where we synthesized case data from actual data in real time and visualized these case data in real time. For the second task, we chose weather analysis, where we tried to visualize how different aspects of weather changed over time. From these, we answered 3 questions. First, can we use DDS metadata to replace stored data sets? Second, can we build workflows for domain-specific analysis tasks? Third, can we build domain-specific data visualizations? These 2 tasks were selected since they were from different domains and hence catering for different applications. For the eye movement analysis task, we started with 2 data sets with eye tracking data at 1000 Hz and 60 Hz. So we replayed eye movement data from different subjects, modes, tasks, and positions, which are the different perspectives that these data sets were created on. Next, we obtain eye movement analytics in real time, visualize these eye movement data and analytics, and also optionally, we synthesized eye movements from the analytics data itself. The workflow shown on the bottom shows how the data arrives from the data marks in node and traverses through the workflow, and outputs from different analytics are sent to visualization nodes, which populate the operations dashboard shown on the right. So here you could see that it gives the option for you to select several streams, confirm the selection, and once these streams are active, the workflow processes the incoming data and the outputs are pushed onto the visualization node. For the weather analysis task, we chose fantasy climate change dataset, which provide temperature, dew point, humidity, and wind speed measurements over time. So here we replayed the weather data from different cities and states. And our workflow calculated moving average analytics in real time and visualized these analytics. So here you could see that just by changing the nodes in the workflow, you can come up with an entirely different visualization, which is shown on the right. Next, we evaluated the performance of our frame. For this, we selected 4 different transformations from the 2 workflows and ranked them according to their demand for compute and the demand for output storage. So the 4 transformations we selected are a mean computation, a threshold computation, a derivative computation, and a smoothing function. We sent 100,000 samples at 50 Hz through these nodes and computed their mean latency, the inbound data size, and the outbound data size. We did this in both the replay mode and live mode. And as you can see, as the demand for compute increases, so does the mean latency. And also, as the outbound data size increases, so does the outbound volume. However, Given that you have metadata that describes the frequency at which data is coming in and the frequency at which the data is generated, instead of calculating them during runtime, we propose some heuristics that lets you start calculating it before actually receiving data. So fluidity is a heuristic that we propose to identify computational bottlenecks in a transformation. So it is calculated as a ratio of the expected frequency of sending data out and the observed frequency of sending data out. For instance, if the ratio between the observed frequency and the expected frequency is low, that means the output is slow performing. And similarly, if the two are the same, that is an ideally performing transformation. So the growth factor is a heuristic for the change in data volume. It gives an indication whether the output generated is a compressive output or whether it's an expansive output. So as long as the output volume does not depend on the value of the data, the growth factor is defined. However, for a transformation like a threshold, where the number of output data points depend on the actual value of the data, this heuristic is not defined. Using these heuristics, we ran the same experiment that we ran earlier, and instead of just computing the mean values and the volumes, now we also computed our heuristics. So here you can see the first transformation, which has the lowest latency, has a fluidity equal to 1. However, the last transformation, which has a very high latency, has a fluidity equal to 0.742, which is less than 1. So the fluidity heuristic works as we expect. Now for the growth factor heuristic, we can see that the first function, which has the least output size, has a growth factor of 0.02. And similarly, it has an output volume, which is very much less than the input volume. The third transformation, which has the largest outbound size, we have a growth factor of 2. Essentially, the output volume is double the input volume. And also note that for this second transformation, the growth factor is undefined. This is because the output volume depends on the value of the input data, since it's a threshold function. So in the future, we plan to conduct a user study to assess the workflow design experience and the perceived benefits of metadata propagation. We also plan to release a domain-specific subflows to the public and to analyze the compatibility of DDS with well-used metadata formats. We also plan to explore ways to simplify the creation of resolvers, more communication methods, adding subflows for time synchronization, and integrating a workflow engine for distributed execution. So in summary, StreamingHub improves the reusability and reproducibility of research. We propose a metadata standard DDS for propagating metadata from datasets and streams. We also used a visual frontend to build stream-based workflows and dashboards. We were able to successfully conduct 2 case studies using StreamingHub. And our results showed that using StreamingHub simplified the research process and let us build reproducible experiments and in turn generate verifiable results. Also, the platform heuristics were useful to take informed workload distribution and chaining decisions. In the future, we plan to create a public repository of reusable workflows. Also, we plan to improve communication mechanisms in StreamingHub and support distributed execution. Thank you very much for listening to this presentation.